Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Let me welcome you to our today's talk brought to you by the Oxygen Alliance. My name is Victor Mzembe. I'm the medical engineer for Oxygen Alliance, and I'm your host today. I'm hosting this call from Lilongwe, Malawi. So we'd like to know where you're joining us from, our attendees. So you can do that by typing your name as well as location in the chat. For Oxygen Alliance communications, you can drop your email in the chat as well so that we can add you on our emailing list. So today we are continuing with our medical imaging equipment series, and this will be our fifth presentation on this topic. So for this talk, the Oxygen Alliance has partnered with Pacific Diagnostics to bring you their expertise on this topic on understanding the ultrasound imaging systems. So our presenter today is none other than Urjit Thakur, who is a service biomedical engineer for Pacific Diagnostics. So just take note that during the presentation, there will be 4 questions that will be launched. So I encourage you to participate in the voting process so that we know your engagement in the presentation. Additionally, there will also be an attendance form that will be dropped in the chat. So just make sure that before the end of this call, you fill the form, because it will be important for you to get your certificate of attendance at the end of this medical imaging equipment series theme. Yeah, so without wasting much of your time, I will hand it over to our presenter today to take us through this presentation, who is none other than Urjit Thakur. Over to you, Urjit.
Okay, thank you, Mr. Victor. Thank you so much for the nice introduction. Good evening, ladies and gentlemen. I would like to present this short presentation on understanding ultrasound systems. I'm Urjit Thakur. I'm a biomedical engineer with Pacific Diagnostics. I've been working as a biomedical engineer for 10 years. So I hope whatever we speak today assists you as well as fellow biomedical engineers. And let's see how that goes now. Thank you. We can start with the basic definition. As you all know, an ultrasound is an acoustic energy in form of a wave. So it generally has a frequency above 20 kilohertz, which is above human hearing range. And the ultrasound is in a way of using sound wave to look inside the body. So in basic terms, an ultrasound is an imaging test that uses sound waves to make pictures of organs, tissues, and other structures inside your body. So going to the principle of ultrasound, ultrasounds are created using ceramic crystals, and the vibration is what creates them. So when these crystals vibrate, waves travel through tissue and are partly reflected at each tissue interface, which is what forms the image. And these crystals are known as piezoelectric crystals. And the principle is the piezoelectric crystals, when electric current, generally an alternating current, is applied to piezoelectric crystals, they start to vibrate, and these vibrations generate sound waves with frequencies between 1.5 to 8 megahertz, which is generally what is the ultrasound. So the principle of ultrasound also, the following phenomena occurred when the ultrasound propagates through matter. So the first one is refraction. So refraction in ultrasound occurs when the ultrasound waves interact with structures, interfaces within the body, and at angles higher than 90 degrees. Diffraction is the spreading of waves as they pass through and around objects. As you can see on the right side of the image, you can see the crystal diameter wavelength, and then there's an aperture below. So when that wave forms that way, is what is the divergent waveform, that is what's formed by diffraction. So when you have when you see the screen on the ultrasound, you see a sector size image. You see a sector generally. And that is why this is due to this phenomenon. Then you have attenuation, which occurs when the ultrasound passes through the organs and soft tissues. The amplitude of the ultrasound wave reduces. So basically on the image, you have slight bright spots, So these the brightness depends on the value of the amplitude. So the higher the amplitude, the higher the brightness. So that's affects the brightness. And then finally, we have the scattering effect. So scattering is when the ultrasound waves strike structure with different impedances surrounding the tissue. So that's why then sometimes you get darker spots within the images. So the darker region is due to the scattering of the ultrasound, and the brightness is due to the attenuation of the ultrasound. So then we have the generation of the ultrasound as well. So the ultrasound waves are both generated and detected by the piezoelectric crystal within the transducer. So the crystal itself within the transducer deforms under the influence of electric field and vice versa. Vice versa meaning when the sound wave propagates within the body and comes back, so then it is deforms again. So this, when an alternating voltage is applied to the crystal, a compression wave with the same frequency is generated. So the voltage is what determines the frequency of the wave. So, and generally the material used is PZT and PVDF, that is polyvinyl fluoride, which is inside the transducers. Okay, now the relationship between frequency and resolution. As you can see on the slide, you have these images. You have a 4 megahertz and a 7 megahertz image of the ultrasound. So the frequency with the higher, the ultrasound with the higher frequency, the image resolution is higher. So the higher the resolution, the higher the frequency, the higher the resolution of the ultrasound. So the clearer the image and the crisper the image, which is, as shown in the diagram, the right side image is a bit clearer than the left side due to the frequencies. Also, frequency has a relationship with the penetration. Now, the higher frequency does give higher resolution, but at a cost of penetration. In the sense that, as you can see from the image that I've shown on the right side, because the 1 megahertz frequency is less, it is penetrating all the way to the bone, almost to the bone. But as you can see on the 3 megahertz ultrasound frequency wave, that it is only penetrating till the muscle. It's not reaching near the bone. So the lower the frequency has a longer penetration, and the higher frequency has less penetration. So as when you're using the ultrasound, you're supposed to vary these three factors when you're trying to get the image. So you have to vary the frequency in such a way that you can compensate for both the resolution as well as the penetration to get the image of what you need and to get the best quality image, what is required. And as I said, ultrasonography is, or diagnostic sonography is an ultrasound-based diagnostic imaging technique used to visualize internal body structures. So, as I had said in the introduction, is like an imaging test that uses the sound waves from the ultrasound to create the images. Now, moving on to the imaging modes. There are three main imaging modes that's in grayscale imaging. There is the A mode, the B mode, the M mode, and there are various things under Doppler imaging, which I will now explain in detail. So A mode, also known as amplitude mode, is the simpler form of ultrasound imaging, which is based on the pulse echo principle, meaning you send a pulse and the echo comes back, and that is, it displays that a single dimension, you get one-dimensional information. So generally you use this mode only to measure distances. You don't get much from it. And it's only useful for echo and cephalography and echo ophthalmoscopy. So as you can see from the image on the left, you can see the probe is placed on the patient. The pulse is sent, it hits the organ and it comes back. But the only thing it gives is the wave. That wave is what you use to determine distance. That's about it. So it's not very useful in the imaging aspect. Then now we have the B mode, which is also known as the brightness mode. So this, as you can see from the image on the left side, it gives a two-dimensional information about the cross section. So generally this is used to measure the cardiac chamber dimensions and assess valvular structure and function. So this is the actual image that you make when you're using the B mode. As you can see the organs, you can see the liver, you can see the vertebrae, you can see all the organs displayed on the image as I've shown. So this is what we generally use for ultrasound imaging and what the radiographers use generally. Now we have the M mode. M stands for motion. So this basically represents the movement of structures over time. So why we use this is to see, measure the chamber's dimensions for the heart. You can see the image on the left as I've shown. You have a 2D image above, that's for the B mode, and below it is the M mode, which you measure over time, and you can see the different organs and how it's reacting. So in the M mode, you can see the blood vessels, so the posterior wall, and how it's reacting over a certain period of time. So that is what we use the M mode for. Mostly in the cardiac applications is where it is used. Yeah. Then we come to Doppler imaging. So Doppler imaging is a term used to visualize velocities of moving tissues. So Doppler ultrasound evaluates blood velocity and flow through the blood vessels. So generally in cardiac, if the doctor wants to know the amount of blood flow through the vessels and organs, this is where the Doppler imaging comes in hand. So blood flow through the heart and large vessels have certain characteristics that can be measured using these Doppler imaging. So this technology is specifically for visualizing velocity and moving tissues. So as I said, there are different types of Dopplers as well. There's a continuous wave Doppler, there's a pulse Doppler, and there's a color Doppler. So the first one, going to continuous wave Doppler. So in the continuous wave Doppler, you have two crystals. One crystal sends the signal, the other receives the signal. So one crystal consistently sends out a sound wave of a single frequency, and the other consistently receives the reflected signal. So it is sent, so it's continuously sending and analyzing. That's how you get continuous imaging. So that's how you're observing the movement or the velocity of what the organ you're trying to decipher, or you're scanning. Then we have pulsed wave Doppler, slightly different than the continuous wave, in the sense that it sends the pulses in short bursts, and also it uses the same crystal to receive as well as send the signal. So what this does is you get a 2D image formation due to it sending the signal and receiving it from the same crystal. Then we have color Doppler. Okay, so now this is on the, as you can see on the left side, this is a color Doppler. You have two colors that have been visualized. It utilizes pulse echo Doppler flow principles to generate a color image. The image is superimposed on the 2D image. So the initial image is drawn out, and then you superimpose the second image on it. And as you can see, the red and the two colors you can see, that is a red and blue that are displayed. So the information, the red displays the direction of the blood that is flowing, and the red displays the velocity of the flow. So it is used for general assessment of flow in region of interest, generally in organs such as the liver, the heart, or certain organs that you need to see. So it only gives descriptive of semi-quantitative information on blood flow. So it will give that much information on certain basic information only. Then you have the power Doppler. So this, as you can see, the image compared to the color Doppler is much more detailed as opposed to the color Doppler. So it is more sensitive than the color Doppler in detecting blood flow. So it gets those images that you cannot get with the color Doppler. So this gives more detailed information on blood flow as opposed to the color Doppler within solid organs. That is the liver, the heart, and whichever organs you're trying to evaluate with the ultrasound. Okay, now we will go to the ultrasound machine. This is how generally the ultrasound machine looks. So you have the monitor, you have the keyboard, as you can see, where you can adjust the settings, where the radiograph adjusts the setting. Then you have the printer at the below it. You have the transducer holders. You have the transducer cable hook as well below. You at the lower half of this, you can see where the transducers are connected. So that's where your boards, your CPU, all your processing, where the processing and image processing takes place. And so this is just the higher end, this is basic higher end model. So there are certain external options like the ECG port. Then you have the auxiliary continuous wave Doppler transducer port, and you have the continuous wave transducer port as well. And within that body as well, you'll have the boards that do the back end, front end of the machine. Front and back end I'll explain ahead when we get to the machines in detail. And also this is how the basic ultrasound looks like. So just for convenience, I am going to talk in detail about three systems. So you have the Accuzon NX3, you have the Accuzon Juniper, and the Accuzon Redwood. So why I've chosen these three systems is because I have gone for the lower end, the mid-range end, and the higher end machine. So you can explain and you can understand the differences of these systems and how they vary as well, and when they're used and what specifically when it would be suitable for a customer to use which machine for their setups. So moving to the first system, this is the Accuzan NX3. This is the lower end model from Siemens. This is a very old model. I think it was launched back in 2011 or 12, if I'm not wrong. So as you can see, this has 4 transducer ports. It has the printer as well, the keyboard, and the monitor, as you can see, as I've shown from the previous image, was adjustable, but this one is not flexible that way. So certain options are not there in this as opposed to the higher end machine. So giving the basic explanation, so is, as they have said, it is a system that is platform driven by efficiency and built for performance. So it's more tailored to the lower end needs. So where form meets function, the result is a Newton smart. So basically, this system was went out advice for a lower end customer where he just basically needs to do basic scans for the abdomen, OBGYN. So nothing advanced would be done on this system, such as cardiac scanning or high-end 4D, 3D options. These options are generally not available on this system. So this is just a basic model that's just used for basic scannings. Then you have the Accuzan ultrasound system, Juniper, sorry, Accuzan Juniper. This is a slightly higher, this is a mid-range system. As you can see from the differences as well, you have the adjustable monitor. You have more, the holders for the probes are more. So you have 6 as opposed to the previous one where you had only 4. And also, as you can see from the design, they have put the holders to the side, as in the connector, the connectors for the ultrasounds on the side. This is to prevent the cables from getting dragged and damaged as well from the front, so nobody would touch them directly. So this is more of an architectural advantage. So now moving on to the machine. So as I said, that the system of the ultrasound, there is a front end and a back end system. So basically the front end is where your connector is connected. So this is where your higher system sensitive and specific for tissue differentiation. So basically that's where the transducer is connected and where the image is formed. Okay, so the image is formed there and is taken into the system. So then you have the efficient signal processor that sends the data to the back end. So your back end is where your data is then converted into the image that you see onto the monitor. And also because this is a higher-end machine, the image processing time is faster as opposed to the NX3. So your scan time is reduced by quite a bit as opposed to the NX3 because the processors that are being used in this machine are much better. Now then you have the very high-end machine, that is the Redwood. As you can see, this one also has only 4. This one has 4 connectors, and also as you can see from the body, it's slightly wider than the Juniper. So the boards used inside have much more advanced technology. It has a higher graphic card as well. So your display is more clearer and the pixel rate's higher, as well as the probes as well are more in this system. You get 16 different probes on this ultrasound as opposed to the previous 2. This is because it gives more options as opposed to the first 2 that I talked about. As I said, it's a comprehensive suite of over 16 transducers supporting a diverse range of clinical applications. And the super image clarity. So the technology in this is that because it has a higher end processor, as in the back end is much more advanced than the graphic card. So the contrast resolution is much better. So you can differentiate the anatomical structures much better in this system. So it increases the exam quality and consistency. So different users using it will not tamper with the results. So it's not that someone very well-versed or somebody who has worked for much longer will produce a better image because the technology compensates for that as opposed to the first 2 systems. So now moving on to transducers. So as I was talking, the transducer is basically a device that converts the energy from one form to another. It's an electronic device. So in this case, the ultrasound transducer converts the electrical pulses into sound pulse and sends these pulses within the body, and listens for the returning echoes generated by the tissue interferences, and again converts the sound pulse back into the electrical signal, which is then processed into the image that we see. This is the basic how the ultrasound transducer probe looks like, architecture. So you have, as number one, you have the acoustic membrane. Behind this is where the crystal is, the piezoelectric crystal, as I said. Then you have the transducer housing, where the cables are connected, the electrical cables that send the signal into the piezoelectric crystal. So the transducer strain relief is basically the rubber that prevents the cable from being damaged if in case the transducer gets bent or you put it at certain angles. So this prevents the cable from getting damaged, and also it protects the cable from water entering into the transducer housing. Then you have the cable, and then you have the strain relief, connector strain relief, which does the same purpose as what the transducer strain relief does. And then you have the connector that is connected onto the system. Now we have 6 different basic probes that we use when generally using the ultrasound. You have the straight linear array probe, you have the curved probe, you have the phased array probe, the endocavitary probe, 3D and 4D probe, and the TEE probe. So first we have the straight linear array probe. So this is designed for superficial imaging. Superficial imaging meaning imaging that is just below the skin or around, that is, it will not penetrate too deep. So that's why the probe has a very high frequency of 5 to 13 megahertz, which provides better resolution and less penetration, which I had explained in the relationship between frequency and penetration and resolution. So because this has a very high frequency, it will not penetrate as deeply as you'd want. So it's just for the superficial scanning. So, and also because it's not curved and it's rectangular, the image will not be in a sector, it will be in a rectangular shape. And because it is in rectangular shape, the crystals are aligned in a linear fashion within a flattened and produce sound waves in a straight line. So the wave propagates in a straight line, and so there's no diffraction occurring on this ultrasound, on this probe as such. Then we have the curvilinear probe, also called the convex probe. So this one is used for scanning deeper structures. So generally within the abdomen, if you want to scan deeper within the body, you will generally opt to use this probe. And as opposed to the previous probe, you can see that the frequency is between 1 and 8 megahertz. So by default, the penetration will be more and the resolution will be less as opposed to the linear probe. And the image created is in a sector shape. This is because of the curved surface. So the wave propagates in a curve. So you get a sector shaped image. And as I had said, it is generally used in abdominal and pelvic scans. And the crystals, as opposed to the first transducer, are arranged along the curved surface, which results in a wide field of view. And you have the phased array probe. In this, the crystals are grouped closely together. So you have crystals tightly packed within that small head. So the sound wave originates from a single point and they fan outwards, creating a sector image as similar to the previous array probe. And it has a smaller footprint than the curvilinear probe because of the size of the probe. The probe is very small, and the frequency is between 2 and 8. So again, it has penetration as well. So this probe is generally used for cardiac imaging and imaging between the small spaces between the ribs. Then we have the endocavitary probe. This has a curved surface, and as you can see from the design, this is generally used for very specific orifices within the body. Like you have the endovaginal and these probes. So this also has a very high frequency, and because it can be inserted within the body, so you can go close to the point you want to scan. So that's why the frequency is higher. So you don't need penetration as opposed to the previous 2 probes. And the probe elongated shapes allowed to be, as I said, because of the shape, it can be inserted very close to the anatomy of the body that you want to evaluate. And because of the curved surface, you get a 180-degree field view. So, and because of the high frequency, the resolution is superior, which is what I had said as well. So as I said, we have the endo-vaginal probe. So this is generally used for GynAC applications and OBGYNs. Generally, the OBGYN uses these probes. Then you have the 3D and 4D probe. So this is similar to the 2D probe, barring a moving array. So the images are captured from various angles. So because there is an array, it shoots the X-ray, the ultrasounds at different angle. So the waves propagate, and then it's swept within that space. So it manufactures the 3D image using that. Then you get a live image. This generally is also used in GynAC, from what I know, and you can see the child's face, and also used for gender to know the exact gender of the child. And finally, you have the TEE probe. This is the transesophageal probe. This is a cardiac probe, and this is the one probe which is inserted directly within the body. So the patient has to swallow this probe, and it is put in through the esophagus. And this probe travels in 4 different directions. As you can see, there's a handle, that knob. So that is what controls the movement of the probe. And this is used generally in cardiac if you want to image the heart internal from within the vessels. So this is inserted, and this probe is used for that. So it gives a complete live image of the heart. Now, as I was saying, as fellow biomedical engineers, maintenance is the most important part of any equipment that we handle and install. So this will be basically what maintenance requirements are there for an ultrasound. So I have broken this down into 3 things, that is daily, monthly, and yearly. So if we maintain the equipment, by default, the machine will last longer. So less breakdowns and better service for the customer. Okay. So for daily, this can be done by the resident biomedical engineer at the hospital, or it can also be done by the user, that is the radiographer. He just needs to make sure, okay, the first thing he needs to make sure, because he's the user, is the probes are clean every day in the morning, or when after he's done using it, that is free of gel. What happens is generally, I have noticed at hospitals, is when the radiographer uses the transducer, he leaves the gel on sometimes, and maybe he will not use the machine for some time before the next patient. So that can also damage the rubber on the transducer, and also dirt can accumulate on that transducer, which can lead to bad imaging as well. That is 1. 2, as you all know, ultrasounds generally have a UPS, that is a battery with it, that are installed onto the system. So if your ultrasound is plugged in 24/7, what happens is that battery gets damaged over time. So it would be advisable that on the long run, you always unplug your system at the end of the day and leave it unplugged. So the next day when you start it, the UPS battery charges again. So it gives a longer life to that battery as well. So then we have the monthly. For monthly, what we generally do is when we head to site, we blow the machine and clean it in the interior parts, and there are air filters as well that are within the ultrasound. So you can remove those physically, clean them by blowing them, or also by just wiping them once and leaving them to dry and then putting them back within the system. So this also prolongs the lifeline of the life of the machine. And finally, we go to the yearly. Now, this is what generally we do, it is called preventive maintenance service, PMS. This is to be done by the trained service engineer, the person who has supplied. So suppose I have supplied a Siemens machine, I would be doing this every year. So there is a protocol that is in place where I have to check certain things within the machine, that is the voltages, if there is any leakage voltage within the plugs, or if there is a leakage voltage that is going within the machine, that is 1. 2, I need to also check the life of the battery that is present on the UPS. So if the battery is faulty, or if the battery's voltage that is output is not correct, that needs to be replaced. And also, as I had said, this is it has a BIOS, it has a CPU at the back. So there's a BIOS battery as well that we generally replace once every 2 years. So you need to check the voltage on that as well when we are doing these maintenances. So these are important things. So as I said, this maintenance needs to be done every year so that the machine is assessed, and also we can prevent errors in the future. that occur by constant use of the machine, and also help increase the lifetime of the system. So it can be used for a longer time. So the more you maintain the machine, the longer it lasts. It's like how if you have a car, after a certain number of kilometers, you take it to the garage for a service. So it's the same thing with our systems as well. We have to keep maintaining them, because the longer you maintain the system, the longer it will last and the happier the customer will be in the long run. Now we come to planning for acquisition of an ultrasound. So now when you're planning for an ultrasound, or as a salesperson, as a biomedical engineer, what do you need to know? One, when you meet the client, what you need to know is what the client needs the ultrasound for. So if he going to use the ultrasound for basic scans, so for basic scans and abdomen scans and standard scans, then you don't need to provide him with a very high-end machine. You can quote him on the low end, like I had explained for the NX3. It can be that. Then, okay, suppose if your customer is a doctor who's a cardiac specialist, so he would need a high-end machine where he needs to do cardiac scans. He would need the Dopplers, the power Doppler. He would need to know how his patient's heart is. So for those customers, you could suggest a higher end machine. So the important thing is you need to know what your customer requires before you can supply him with a quotation on what system he needs. That's one. Two, when the customer has decided to acquire the system, what we suggest is, one, he should always have a room with a AC. Why? Because by default, this reduces the dust within the room. So this reduces the damage to the transducer probes as well as the damage to the machine. So there's less dust within the machine. So there's less chance of damage to the boards within the system as well as the transducers. And also, we always advise the customer to have a UPS. So that means the system should be on UPS. So in case if there's a power surge, which we have a lot of here in Africa, it can damage the boards as well as it can also cause to corruption with software. So this also at the end of the day causes inconvenience to the customer as well as to us, because then we as the engineers have to go, you have to order the board, you have to replace the board, and reloading the software also takes a bit of time. So this all can be avoided with the UPS. And finally, from an economic standpoint, that is, this is now more to do on the customer side. If the customer wants to buy a high-end machine, but if he is not scanning those many patients to recover the amount of money for that machine, so it would be, so in hindsight, it would determine if you will be using a higher end price point or lower end price point system. So that is for you as well to judge with the customer that how many patients would he be expecting to scan. So then what this does is this makes it easier for you to sell your machine as well in the long run. And also because if you assist him this well, he will always buy from you for a longer period of time. Okay. These are the basic problems that we encountered with ultrasound, or I have encountered with ultrasounds. Due to the machine, not as I said, the UPS is very key. If your machine is not on UPS, it can lead to damage in software as well as damage of the boards on the system, as I said earlier. Secondly, in government hospitals, mostly this is noticed, the cleaning is not done thoroughly. So having an AC, not having an AC can lead to dust in the system, which damages the cooling fans as well as the boards over time. So over time, then again, this becomes an added cost to the customer as well as an inconvenience to you. And then the last one is, as I said, if the probes are not clean, so the user, this is more on the user than us. The user needs to be told repeatedly that he needs to make sure his probes, the probes for the system are kept clean and proper. So the damage to the rubber is not as substantial. So the probes will be used for longer. And also it leads to better readings on the system because the probe is kept clean. So, okay, now finally troubleshooting tips. These what I do generally. So generally when you get calls, maybe 60% of the time is the machine is not turning on. So what you need to do is you can check if the plug and the switch are okay and functional first of all. And you can also check if there's power coming to the plug. Then you can check the fuses within the system if a power surge might have blown one of the fuses. And the last is to check the power distribution board within the ultrasound itself. Also, this is less troubleshooting and more of an advice thing is every system, I always take backups after every 6 months of the patient database, the licenses, and the system configuration. So what happens is if tomorrow by chance the software gets corrupted within the system and the customer wants the data back. But because there is no backup, this data is not there. Those customers we generally advise them to take backups, but they generally don't. So it would be advisable that you can take this backup. So in case if he ever needs it, oh, okay, you have this in spare. And finally, another thing is when the probe fails, you can remove the probe, blow on the connector end and remove the dust. Generally, this helps sometimes. And clean the transducer end with the cleaning agent to remove the dust. Reconnect it, restart the system, reconnect it, and then this generally, the probe generally starts functioning. That this works most of the time. Thank you. I think I can hand it back to Mr. Victor.
All right. Thank you very much, Vijit, for that wonderful presentation. And I guess that was the last part of the presentation.
Hello?
I think Victor just lost the network there. But then the floor is now open to questions. So if you have any questions, you can ask either in the chat or you can raise your hand and we'll address you. Thank you.
Okay. If you have a software issue or a board issue, okay. For software issue, generally, the supplier, that is if it's a Siemens machine, you generally have the software on a disk preloaded. So you have to basically reload the software from scratch. After you reload the software, you have to input the licenses and then the system, you test it again. That is why I suggested that you take the backups of the licenses and certain things. Okay, how do you identify the names of the boards? Okay, for that now is, how do you identify is when you open the board, you will find generally at the back, there is one board, that's the back end board. You have all the boards connected on it. So you have there, okay, it's, from machine to machine, it varies, but I'm just giving you for the Siemens. We have 3 boards on that. You have the input output board. This is the front end part. Yeah, this is where the connector is connected and where the signal is processed. After that, you have the processing board that converts this signal, this sound, the data back, and then you have the processor board. Okay, so you generally have 4 boards, and the higher the machine, you have one graphic board as well. So those you can identify basically when you see. You'll have to open the system and see, but I can then send you the images and how it looks like if you want it in detail. But yeah, that's how it looks like. That's how it is generally. How the archaeology, how the architecture is, sorry.
Okay, so I guess, hello, Jit, I'm back.
Yeah.
I guess you were addressing the question which has been posted in the chat, asking about if you have a software issue or board issues, how do you address them, and how do you identify the names of the board, right?
Yeah.
Yeah. So good luck. I guess you have been answered. If not, if you need more question, just write it in the chat as well.
Yeah, sorry for me, Mr. Jimmy. For the 3D or 4D image, you have to have a 3D probe. Without that, you cannot. Will not. That probe is made for that only. Okay. Then. Sorry. You said something about the printer part. Okay. Yeah. Sorry. I apologize. That is on me. We have the printer connection and setup issues. Okay. What happens is, generally when the printer is provided, the CD comes with it. You get a CD. Like when we install the printers for our systems, we generally install a Sony printer, sorry, and the setup disk is there. So there is a way to install it, but I get what you're saying is, I will next time it needs to be included. Yes, that's correct. But generally you have a CD that provides the what do you call it? The software. So you have to install that software separately, and then from the service page, you're supposed to set up the printer externally. So externally, you have to install the driver first for that printer specifically on the system, and then you connect the printer. The printer does not connect automatically, but that disk is provided by the supplier. Okay. Mr. Enoch, I can send you the PPT if you want it. You can just send me your email ID. I will send it to you.
Hello, Jit, can you hang in there?
Yeah.
Yeah, so I will be reading out the questions for you. So I will just take for the one from Enoch asking about the PowerPoint presentation. So actually, we post the recording of the session on our YouTube channel. So the easiest way to access the presentation is just to go and visit our YouTube channel, and you will find it there by tomorrow evening. So there is another question from Arroyo, I think Arroyo Debra, asking, how frequently have you recommended cleaning the keyboards? Is the ultrasound keyboard very sensitive to dismantling?
Okay.
Or are there any issues seen when servicing the I can see she has posted a standard keyboard. Is that American or British? I don't know, but it's a keyboard format. No, that's their question. Should I read it out again?
Sorry, I can see it. How frequently have you recommended? Okay, now for cleaning of the keyboard, I would recommend once a week. The user can just wipe it. That because I don't think as such, or you can just wipe it. The user, as in the radiographer, should be wiping it regularly. But you, as the biomedical engineer, once a week you can wipe it and blow it. That's fine. And also, the Accusant keyboard is not that sensitive. Only thing is, do not wipe it with the very wet cloth, because water could seep into the buttons and cause an issue. So I would recommend just wiping with the slight alcohol-based product, so that the alcohol dries off, so that nothing seeps in. And also, when you do the monthly maintenance, I would recommend blowing the keyboard as well.
All right. So there is another problem from Tibet. They are asking, what's the problem or risk of using focus ultrasound? That is the miniature and pocket type for trauma scans.
Okay, Tibet, what I would advise is, the issue, it comes down to the same thing. The handheld ultrasound, the image will not be of that quality as what you would get on a normal machine, not the normal ultrasound. One is because, again, it comes down to the, as I said, as I explained, for the penetration and the focus and the resolution. So the image quality you would get on the handheld or miniature ultrasound is not going to be the same as you'd get on a standard ultrasound. So for trauma, suppose if you're scanning the patient and you need to see certain things, maybe the image would not be of the same detail you would get on a normal ultrasound, and maybe then it would hamper the diagnosis for the doctor. So the image would not be the same. So the image quality would be much different. So it would be harder maybe for the doctor to assess, as opposed to an image which is better on what the situation for the patient is.
Yeah, all right. So there's also another question from Jimmy asking, how can I use an ultrasound machine in telemedicine? So I would just take that question.
No, yeah, for telemedicine, as Siemens, what we do is, for telemedicine, is we have a Siemens, we have the hospital. What we do is we connect the hospital on the PAC system. So what happens is, then the image is transferred to the archiving server, and then from there you could send the images, if the server is on the internet, to the doctor that needs to see it. That is how you can use the ultrasound machine in telemedicine. But for that, you need your system to be connected to the PAC server 1 using the cable, and then your PAC server also needs to have internet for it to send the images to the doctor if he's not within the same region, or if he's, like, suppose abroad or anywhere. Or if it's within the same hospital, then you can just use the PAC server itself. So suppose if the technician scans it within one room and the doctor is sitting, let's say, in another department, so the image can be sent directly then, provided the system is on the PAC. So you have, like, the the LAN cable connectors at the back as well on our systems. Thank you as well, Mr. Lloyd. Thank you for this opportunity. Thank you all. Nice speaking with all of you. I hope I have assisted you with my knowledge.
Thank you very much for being on board. We loved your presentation.
Thank you so much. Hopefully this has cleared everyone's doubts, or at least assisted you in some way. So thank you very much.
Our audience, reaching that extent, we have come to the end of our today's session. So thank you very much for attending this session. So we urge you to be on the lookout for the next session on the same medical imaging equipment series. So we thank you for today, and I am wishing you a good evening.